live now. Let's also stream to Twitch as well. Let's freaking go. So, welcome to my practice stream. My name is John. If it's your first time here, welcome. We are going to be practicing mathematics today. We're going to be practicing linear algebra as usual. Not as usual. I do practice other forms of math. I promise you all. I promise I do. And soon, we're going to be adding another series in math. We're going to be adding basic mathematics very soon here. So, but first, today is another day with linear algebra. We're working on complex scalars today. So it turns out that linear algebra applies over any field, not just over the real numbers. And in particular, we often work with the field of the complex numbers. The complex numbers are the real numbers adding the square root of -1, which is we call I. That's the label that we add. And so we are imagining that there is a solution to this parabola x squared plus 1 equals 0, right? In the real numbers, there is no solution to x squared plus 1 equals 0. But if we imagine that one exists, we get a very beautiful, complete field of algebra, a complete form of algebra where every single polynomial splits as linear factors. Every polynomial has n roots. Ooh, I don't think I've seen that book. Basic Mathematics? Yeah, dude. My thought right now is that we're going to get much more proof-oriented soon in this stream, and I'm very tempted to completely replace Fraleigh shortly and replace Fraleigh with basic math, and this is going to be high school mathematics, but proof-oriented high school math. And I'm considering doing this in conjunction with Axler, potentially. I don't know. That's an option. But what's up, Arad? How's it going, bro? Okay, so complex scalars, the algebra of complex numbers, matrices and vector spaces over the complex numbers, eigenvalues, diagonalization, and Jordan canonical form. So, good stuff today. It's going to be chill. So, where is... I'm also multi-streaming today to Twitch, so if anybody prefers Twitch for any reason, then feel free to watch me there instead. Hey, what's up, Zafar? Bro, thank you for stopping by Math Hang yesterday. I'm sorry you missed us. Yesterday I was introducing basic mathematics and a new series that I'm about to begin, which is an intro to proofs in context of high school math. I'm excited, dude. I think it'll be fun. And this is because I'm practicing teaching at the high school level. So I think that'll be fun. Is this linear algebra? Yes. Today will be linear algebra again. I know. You're starting to get antsy for more. What's up? Unpronounceable name, Chris, but I call you Chris. How are you? I'm doing good. It's just a burning memory. How are you? We've got a few people here. Oops. Why doesn't that double tap work? I'm so confused about it. Is there 2 different verticals? Oh, there are 2 different verticals. Look at that. Okay, that would be why. That would explain it. Okay, what's up, everybody? Good to see you all. I've been quite sick recently. That sucks. Math-wise, pretty good. How's interviewing coming along? I just had a really great interview, actually, on Friday. I don't want to get my hopes up too much, but, dude, let's see, you know. Oh no. Oh no, you can't self-study math anymore? Man, it's you and Locke are both giving me bad news about that. Locke just told me in the Discord that he may not be able to join as much coming up, and that's so sad, you know. I enjoy hanging out with you all, but I know, yeah, we need to get real work done. You know, math is kind of pointless and probably detrimental to your salary. Don't study math, kids. Not even once. Not even once. Don't study math. Don't do math. Oh, you're in high school. Nice. Bro, have you seen this book? Nitik, I don't know how to pronounce your name, but nice to meet you, man. I'm gonna call you Nai, if that's okay, or tell me how the right way to pronounce your name. Check out this book. This is high school math, but like a badass, like serious, pure math version of high school math. I'm about to start a series working through this book, dude. Good luck with apples. Yeah, thanks, dude. I used to work at Apple, dude. I used to work there. I worked on iMessage. I fixed a security problem with iMessage. As well as some other really cool things. Alright, so number 6. Express Z inverse in the form of a plus bi for a and b real numbers. Let's copy this over. So here's our first problem in section 9.1, which is just the algebra of complex scalars. Complex numbers, also known as Blackboard C. Okay, express Z inverse. So, high school math people, you might be able to join me for this one. This is kind of a review of complex numbers. So, how do we write Z inverse? If Z is a plus bi, then Z inverse is something else, C plus di, such that Z times, what does an inverse mean? We're talking about a multiplicative inverse. So a multiplicative inverse satisfies a number times its inverse equals the multiplicative identity. So the inverse undoes a number so to equal the identity. Multiplicative inverse. So inverse is like kind of like reverse. If you have Z to revert back to the multiplicative identity, we need to multiply by the inverse to get to the identity. So therefore, we have this equation, a plus bi times c plus di equals the identity. Then we have the distributive property, ac plus, after a little bit of distribution, we'd get AC minus BD plus AD plus BCI equals 1, right? What's up? What's up, everybody? Oh, not even a math student, but you, I just popped up in your recommendations. Let's go, dude. That's great. Yeah, do you like math, though? Even if you're not a math student? Do you like math? Do you watch other math YouTubers? Yeah. Dude, that's cool. Yeah. All right, yeah, you beat me. Okay, so then therefore, here, we need to have AC equals B, we need AC minus BD to equal 1, and AD plus BC has to equal 0, because the imaginary part of this number is 0, right? Okay. Then what can I get from here? How can we derive... I don't know if I've ever tried to derive the inverse of a complex number, and I don't even know what it is right now, actually. I mean, here's some deeper theory about the complex numbers. If I have a complex number, a plus bi, we can view the complex numbers similarly to the plane. We can view a complex number as a vector so a vector always has a length and an angle. Then if we represent a complex number as a point in the plane, we can form a right triangle such that the complex number is r times sine theta plus I cosine theta. Wait. No, I got this backwards, didn't I? Cosine theta plus I sine theta. And I remember that it's I times sine theta because the imaginary part is on the y-axis. So the height of this point is the height of the point is the imaginary part of the complex number, and the height of this right triangle is given by sine theta. Yeah, so if this is A and this is B, then by Pythagorean theorem we know A squared plus B squared equals R squared. And we know that Yeah. If you normalize that triangle to have length 1 along R, that is right triangles, like we have similar right triangles where one of them, the original right triangle, has length R. We can scale it to this smaller right triangle, but this angle is going to be equal, complementary to the other. So then sine theta is ultimately, like, by thinking about right triangles here, we would see that the height A is R times sine theta. And this shouldn't be A, this should be B, because the point is A plus BI, right? So B is R sine theta, and A is R cosine theta. So then if we have a point, what I'm trying to get at is, if we have a point that has angle theta, and we want to multiply a complex number by another, we need another complex number that scales this point and maps it to the multiplicative identity 1. Here, let's multiplication by a complex number is, so this is R times cosine theta plus I sine theta. We can also prove, I think, that this is also equal to this other expression of z, re to the I theta. Therefore, if I have a z and I want to multiply by the inverse, this would be R1 e to the I theta 1 times R2 e to the I theta 2. And this needs to equal 1. Therefore, R1, R2 needs to equal 1, and e to the I theta 1 plus theta 2 also needs to equal 1. Let's show the intermediate step here. Therefore, R1, R2 e to the I theta 1 plus theta 2 equals 1. Like if you do multiplication of those two and rearrangement, you get that. Therefore, we need both of these to be true. Therefore, since R1 is chosen and we're deriving R2, R2 is the inverse of R1. And what is R1 again? It is the length of Z, which is the square root of A squared plus B squared. And theta 2 needs to... Theta 1 plus theta 2 needs to equal 0. Because the second equation only is true when the angle is 0. So, I'll just write that as theta 1 plus theta 2 equals 0. So, therefore, our new angle that we're calculating for is the opposite of the original angle. Yeah, I wonder if there's a... Yo, what's up, Sumit? How's it going, bro? We won't read what I said. I was thinking about that. I was wondering if there's an algebraic property where we can multiply these, but then we'd get some weird cross terms that I don't know if we can directly get anywhere useful by adding the terms. By multiplying them. I mean, maybe we could add the 2, because adding 0 to anything equals itself. This is now starting to look like this is starting to look like Z inverse and Z inverse conjugate. Like, I think that we are going to get to the complex conjugate in this somehow. Yeah, because right now I'm using like a little more technical power by employing Euler's identity. But I kind of feel uneasy about this. But so if we have a complex number, then the angle that it represents is this, right? Yeah, we're looking for the real and imaginary parts of Z inverse. Yeah, I want to see if we can derive this. So Z inverse is we found the length of z inverse I think that this is not the best way to do this. I just wanted to see how far I can get before I take a look at what's in the book. Do I have... Because right now I'm trying to find a general... Right now I'm trying to derive the general equation for z inverse. But the problem is just asking for a specific calculation. So I think in the section, it will show the solution to the proof for this. How do we do this proof? There's got to be something. Can I take cosine of tan inverse? So tan inverse would get us the angle. So then cosine... I think that this is the right... I think that this works. I'm just going to write that denominator as length of z, or r. Yeah, so whatever the angle is, like tan inverse gets us the angle, and then cosine would be a divided by r. And sine is b over r. So now we have 1 over... r is the same thing as length of z. Yeah, now we have 1 over z squared a... Oh, wait. We're supposed to be finding negative theta. So if this is theta, then we're supposed to be using negative theta here. So cosine is the same, but sine... Yeah, sine has the opposite sign. The opposite sign. Yeah, we missed the sign change there. Yeah, we're getting close. Okay, so a minus bi. And now this is z conjugate divided by length of z squared. Yeah. 1 over length of z squared times z conjugate. I don't know the best way to write this. But this is our claim. And I can double check by just trying it and seeing that it works. So a difference of squares formula. Um, so difference of squares, we get a squared minus b squared I squared over a squared plus b squared, because when you square the square root, they cancel and you get the argument. This is a squared plus b squared divided by a squared plus b squared, which is 1. Cool. So this worked. So I found it, and I used the fact that I can think of a complex number as a vector with an angle and a multiplication of complex numbers adds the angles together. So I don't know if that's like kind of cheating a little bit, but oh, there's another math channel doing an entire series on geometric algebra. Oh, dude, that's cool. Yo, what's up, Locke? JC said you will never come back. Something like that, almost. Yes. Today's the last day I will be a regular here. Bro, that's so sad, dude. It's so sad. You better pop by every now and then, man. I hope that... My goal is that this can be a stream that people can study to. I don't know how realistic that is. I just don't know. But if you're physically in a lecture, obviously you can't tune into a stream while you're in, in a lecture. So... all angles. Interesting. Yeah, have fun with classes, bro. Okay, I want to see the book's proof because I feel I used a fairly... I don't know. I used heavier machinery than I think that you need. I wonder if there's a better way. Okay. So, the book defines definition that the complex conjugate of a complex number is a minus bi. Then z bar is oh wait, equation 1. Why is this next part true? Oh wait, zz bar is magnitude of z squared. Wait. They say if z is not equal to 0, then from this last line, then z times oh, yeah, okay. Yeah, you just divide both sides of that previous equation by z bar. Of course, okay. The way that they substituted for z bar, I found was a little confusing in this writing. I see. If z is not 0, then I would say then the length of this is not 0. So z bar divided by, like, I just don't really like the exact way that they typeset that, I guess. Z bar divided by length of z squared is equal to 1. And so z times z bar over length of z squared equals 1. Therefore, z inverse is z bar over length squared. Okay, and now we get to the same conclusion. I knew that there was going to be some more pure algebraic proof of this that didn't require polar form. So, hey, you're doing linear algebra right now. Let's go, dude. I'm studying to these streams every time. It's great. Hey, that's awesome. That's great. I usually study while hanging out here for what it's worth. Nice. I hope you try it, Locke. What the complex are we doing, by the way? Yeah, we are just, really, in the end, I wanted to just solve these problems. And I was like, wait a minute, what is z inverse again? And I wanted to derive it on my own. And we did it. So now I can compute that z inverse for part A is, I'm going to do 1 over a squared plus b squared is 2 times the conjugate, -1 minus I. So this is -1/2 minus 1/2 I in standard form. And now we're done with this one. And then for the second problem, z inverse is, let's do, z conjugate over length of z squared. Z conjugate is, well, I like to first do this 1 over z, length of z squared is 9, 9 plus 16, which is 25, times 3 minus 4i. And so this is 3/25 in the real part minus 4/25 I. Cool. And we could check if we feel like it. Mathematician sees special case, tries to generalize. um, yeah, more at 7. That sounds about right. Yeah, what's up, Sundar? Yes, I am from the United States, and I graduated in 2012 with a degree in pure mathematics. Then I worked for about 10 years in software, mostly as an iOS engineer, and mostly in the Bay Area, like in Silicon Valley, at big fancy companies like Apple, Lyft, and Google. Nowadays, I am trying to build a few of my own apps, and more so, moving on from that and trying to become a content creator and a high school math teacher. So, yeah, what did you do with your degree in math? Nothing, I guess. No, I mean, you often don't directly use your pure math training if you go into industry, but you indirectly use it every single day. I was fairly good at functional programming and like an ability for abstraction. Like I was better than my colleagues at it in general, like especially when we just keep freaking re-architecting apps for no good reason other than mathematical purity. Like people just like to keep rewriting apps in something that's simpler, more abstract, more mathematical. And I was fairly good at that. Now AI is taking my job, so it's rapidly devouring the entire software industry, and it's just kind of boring. Like I don't really want to work with AI, honestly. FP is GOAT. Yes, FP is. It really is nice. I thought that this whole time that you were an employed functional programmer. You've probably told me this. Did you get laid off or did you quit? Laid off. My entire team got hit by mass layoffs. My entire team, the team next to mine, my manager, my manager's manager, their director above them, like a giant chunk of the org chart. So, I don't know. To me, it's just like a big symbol that the world is moving on from mobile apps, and, the new hotness is AI, dude. The new hotness, all of companies' resources and all the venture capital money is all going to AI now. 9.2, let's do some actual linear algebra now. 9.2. Matrices and vector spaces. With complex scalars. So now we're going to see that all the linear algebra that we've learned so far works with complex matrices, as well as the real numbers, like we've been working before. Find A inverse if A is I, 1 plus I, 1, and I. I believe that our special formula for 2 by 2 matrices still works. But I would not be shocked if I need to take a conjugate somewhere. We can just check, because the inverse is unique if it exists. So we can just try it and see what happens. I mean, we can try this in general. If our matrix is A, B, C, D, or better yet, A1, A2, B1, B2. No, let's just do A, B, C, D. Then A, B, C, D times DA negative B negative C equals AD minus BC. Whoops. Divided by the determinant. What am I doing? So, I squared, let's do this in a side calculation. I squared minus, if I multiply those two, then we have this. Yeah. So I think that it'll be 1 over... So I squared is -1, -2 minus I. Almost made a major oopsie. AD minus BC. And then in the top right, we have negative AB plus BA. Well, BA is the same as AB. In the bottom left, CD minus DC. Bottom right, negative CB plus, negative CB, plus A plus DA. Top right, we use commutativity to get 0. Bottom left, we use commutativity to get 0. Bottom right, commutativity to rewrite. And now this is AD minus BC over AD minus BC times 1, 0, 0, 1. And now this is the identity matrix. And this is assuming that this is non-zero in order to be able to divide by that number. In this proof, we never assumed anything about the numbers, whether they were real or complex. So this works for the real numbers and the complex numbers. The assumptions that we made were places like here to get commutativity. We use commutativity of addition and multiplication. So I think that this works for any field. I believe that this proof everywhere works for any field, because in any field also we have division by non-zero field elements. So this is true like, here's really the claim. If A is A, B, C, D, then A inverse is 1 over AD minus BC times DA negative B negative C. This is my general claim. Just like somebody else asked in the chat or mentioned, like, a mathematician sees a specific question and then I want to just jump directly to the generalization. And I want to do that because it's going to be easier to just immediately write down this inverse matrix. So I could simplify this so that it's all the entries are in a matrix rather than dividing on the outside. But that's just kind of boring and just doing exactly the same type of division problems that we just did earlier. So I'm just going to say that we're done right here. Yeah, what would life be like if this was a non-commutative ring? Yeah, then we need to think a little more carefully, right? Also, in Stucky, in Twitch, what's up, my one Twitch friend? How's it going? I think I missed you, but bro, it's good to see you. Let's take a quick break so I can pee. Yeah, I missed the 1 over determinant. Yeah. Planning to jump on data science ML. Nice. And then return to academia later. Yeah, dude, academia might be all that's left in 10 years. For real, dude. Which jobs are stable these days? Homelessness? Yeah, that's just about it. Google certainly doesn't regret it, although they're certainly facing the consequences of it. Regret the mass layoffs? Yes and no. I don't know if, like, Google stated in the layoffs notice, they stated that the company was prioritizing AI, and that they were hitting, functions, teams that they felt were not necessary to the company's focus and prioritization of AI. And my team was specialists of mobile apps. Like, we were the somewhat specialists who would implement, like, the latest features. Apple announces a brand new feature and we would implement it so that it's ready a few months later. We, in some sense, like, represented mobile engineering at Google. So, I don't know, man. Like, the fact that they hit, like, both of the teams of, like, mobile specialists, to me was, like, a pretty big kind of, like, symbol of AI taking my job. So, all right, be right back. I gotta pee. Y'all, by the way, I'm a classical guitarist. All the music we've been listening to in the background is me. So if anybody wants to follow my classical guitar channel, I also practice guitar live. And I want these to be 2 different study streams. The goal is that they can be, like, co-working, study with me type of streams and content. You might be surprised. You might enjoy it. Like, just hearing somebody at work practicing guitar, it kind of works well because my working session is music in some sense. So, be right back. I gotta pee. Hey, what's up, everybody? I'm back. So here's the next problem. We're going to be talking about diagonalization of complex matrices. So I already wrote this out. A is this matrix, and we're going to find a diagonalization by a unitary matrix. So this is an extension of our previous theorem. Previously, we had every symmetric matrix or real symmetric matrix is diagonalizable by an orthogonal matrix. Now, we're going to extend this to the complex numbers, in which case, now we're going to be talking about Hermitian matrices and unitary matrices. So what is a Hermitian matrix? A Hermitian matrix means that A conjugate transpose equals A, and then unitary says that U times, I think that U inverse equals U conjugate transpose. Currently preparing for an exam which is quite rigorous. Don't get much time to study the subject in beauty. It depends on what you want to do, Sundar, and what you're interested in. If you want to... Which exam are you studying for? Are you preparing for the JEE, maybe? If you want to try to learn high school math, potentially, I think JEE math, really, in more depth, and try to learn some of the beauty behind high school math, you could get this book by Serge Lang. I'm going to begin doing streams on this book, and I think that you might like it. If you want to learn new math, then like new subjects, instead of just going in depth on the math that you've already learned, you could work through Fraleigh. Like, this is an excellent book, the linear algebra book that I'm working through. Or you could pick up some abstract algebra. Like, if you've already learned about vector spaces and you liked the abstraction of vector spaces, to go to the next level, you could pick up, I like Baby Hungerford, but I've heard good things about, what's it called? Man, there's another book that a lot of people use for abstract algebra, and I'm blanking on it. What are the best abstract algebra books these days? What is the book that a lot of people use nowadays? There's so many of them, man. There's just so many. Galleon is what I've heard a lot of people like. So yeah, it really just all depends, man, on what you want to learn. Dominant foot is fantastic if you're ready for it, but I think that you need a little more mathematical maturity somewhere. Like, dominant foot should not be your intro to proofs. Like, dominant foot assumes mathematical maturity and comfort with proofs, and I think it's an excellent book. I think at my university we taught intro to proofs in an intro to abstract algebra course, and then the upper division abstract algebra sequence used dominant foot. So one way or another, dude, you want an intro to proofs, I think. If you haven't already developed your proof writing skills, This is also called mathematical maturity. You need to grow up a little bit. And it's not solving for X. You can do this in so many places. Discrete math. You could look into how to solve it or how to prove it, I think, by Velleman. This is kind of discrete math / elementary number theory. That's a good place to learn proofwriting, abstract algebra, linear algebra with Axler. Abstract algebra with Gallian. You could, if you're interested, start learning analysis. I don't know the best book for this, though, to be honest with you. I've heard good things about this one book that everybody seems to say is like a new classic. Mathematical Analysis, undergraduate book. What is Understanding Analysis by Abbott? I've heard very, very good things about this book. Pick one. Pick whichever subject sounds most interesting to you. But somewhere you need to start developing mathematical maturity. Ooh, from McLean. Yeah, the category theorist. Wow, interesting. Yeah, you're working on the JE. Totally. Any book will do the job, but the thing is here's what I'm trying to recommend. It's like, you need to have some level of inherent interest in the subject to get through something as difficult as proofwriting. Proofwriting is hard. Like, learning how to write proofs is hard. The other one that I'm suggesting that I think wouldn't be bad, that I'm going to start, is basic mathematics. And we'll see. I mean, I don't know how this is going to go, but I think that this can be a really great book by Lang. New series starting soon. And this is high school math, but proof-based high school math. Hey, what's up? Myth Devi in Twitch. Hi, I'm about to write my exams in October, high school, but I know myself and I lack so much on basic information. How can I improve? Yeah, that's a broad question. I mean, it's the same thing. Like this question was, somebody asked, like, how can I gain more mathematical maturity? How can I go deeper and more conceptual? Conceptual math. Or theoretical, or like pure math. These would all be good options. If you want to get some better study habits without making your subject more difficult or something, Myth Devi, nice to meet you. Myth Devi asks, kind of, you're asking for study tips, right? I think spaced repetition is a good one. Spaced repetition. Return to simpler topics and get better faster and study in more depth. For example, exercises that were not assigned. All of these books, every single book in the exercise set, they tend to go easy to hard. And in a school course, your teacher never has time to work and assign every single exercise. That's not a good idea. But if you want to get really, really good at math and get better, you should really just work more problems than what you're assigned. And I think that it would not be a bad idea to work those problems and then ask AI to judge your solutions on that. Like, however you feel about AI, like, learning how to use it effectively. Like, don't use it for your homework problems. Don't cheat. Cheating is bad. Cheating is bad, full stop. But if you're self-studying and you're learning more and you're working more exercises and you don't have a professor grading your homework, I think using AI is a good idea. Yeah. Ooh, a new Rubik's Cube blindfolded world record dropped. Let's go. That's cool. Yeah, Lockheed is learning math for fun as a hobby, which I'm passionate about. I think that math can be a hobby, and not enough people. There's just not enough community, especially out there online, for math hobbyists. Like, there's so many more math hobbyists than there are resources for math hobbyists. There's textbooks, sure, but there's not community, like finding peers to study on stuff with together. Like, there's Discord groups and stuff like that. Maybe that's where it is. I don't know. But the goal of this stream is to try to build a really nice community for math hobbyists. And especially introduce the idea of studying math as a hobby for people. Okay. So I believe that the process is similar. Let's remind ourselves, what are we doing here again? We're going to find a diagonalization for this matrix. The process is similar, identical, question mark? To real valued symmetric matrices. So, we find eigenvalues. We find eigenvectors. Then our unitary matrix is going to be matrices with normalized eigenvectors as column vectors. And our diagonal matrix is going to be the diagonal matrix with eigenvalues in the diagonal. What's your stream timing? Like my stream schedule? Approximately 9 a.m. Eastern Time on weekdays. This is the current stream schedule, but it might change. I believe to like about 8 p.m. Eastern Time, also on weekdays. I might add some night streams as well as day streams. So, yeah. Okay. Again, here's the general strategy. So if this is our matrix, then our characteristic polynomial is the polynomial lambda minus 9. I factor out negative ones and cancel them quickly, like in my head for that main diagonal. And then minus 3 plus I times 3 minus I, right? So that's the complex conjugate of 3 plus I. Lambda squared minus 9 lambda. So then this is going to be 9 plus 1. Yeah, square root. Oh, wait, no, not square root. 9 plus 1. So this is minus 10. And then therefore this splits as lambda minus 10 and lambda plus 1. I like to sort my eigenvalues. So lambda 1 is negative 1, lambda 2 is positive 10. How could I write this a little neater? Because we set the characteristic polynomial to 0, then lambda 1 is, we have two solutions, lambda 1 and lambda 2. Next, we find V, the eigenspace corresponding to each. The eigenspace of the first eigenvalue is the null space of A minus lambda I, A plus I, which is the null space of A plus I, 10, 1 along the main diagonal, 3 minus I, and 3 plus I along the alternate diagonal. This is a 2x2 system of equations. Which one is easier to work with? I guess the second line. So this is the span, like when x is positive 1, then y is -3 minus I. So that is our eigenvector for the first eigenvalue. Then our second eigenvalue is positive 10, right? Yeah. And sure, a minus 10I, 9 minus 10 is -1, 0 minus 10 is -10, and then the alternate diagonal is fixed. Oops. Yeah, I can see if I multiply the first row by 3 plus I, then the second entry becomes 9 plus 1. So the first row is a multiple of the second row. Okay, so let's see. If we let y be 1, then x is 3 minus I. Oops. When we're solving for the null space of that matrix, just as a reminder for anybody who may not have seen this, the first row corresponds to an equation that says this. And then therefore, if I add x to both sides, 3 minus I, y. So at y equal 1, x, when y is 1, then x is 3 minus I. This is what I did kind of in my head in some sense, and you get good at this and practice this process many times in chapter 5, 6, 7 of this book. Yeah, what's up, geometry? Very secret gang. Yeah, it's moderators. Moderators, dude. Yeah, Sundar, thank you for the feedback. I appreciate it. What's up, SB Practices? How's it going? Yeah, I don't care that much, honestly, about viewers and numbers. In fact, the stream's growing quite well. Streaming quality is so much better, dude. Like, the depth and quality of a stream is better than long form. And dude, longs are just much, much better than shorts. Just so much better in terms of quality, I think. Quality / depth. Like, I get to meet you all. I get to talk with people. I get to, you all are spending hours. Like, you spend hours of your attention here. You spend minutes here. And you spend seconds here. Like, streaming is just so much freaking better. in terms of quality and depth. Now, for numbers and reaching a lot of people, it's not the best way, for sure. But also, more importantly, for practice, for like actually building skill for myself, selfishly, because the goal is for me to be getting better at math. Like, dude, it's not even close. Streaming is already significantly better than video editing. I'm making like no progress getting better at math if I'm editing shorts. Like, dude, with streams, it's all math, no editing. Longs, some math, lots of editing. With shorts, pretty much no math. There's like no real math in a YouTube short. And you'd be surprised, but there's lots of editing to make a compelling 60-second short. What else? Yeah, I mean, practice, skill, and effort at the same time for the same reasons. I don't care about big numbers. Yeah. Don't care about big numbers. Yeah. You need a PhD in math to join. Not very easy. You got to be a mock for a minimum of 3.5 years. What does that mean? OMG practice. Yeah, jcpractices, bro. Like, y'all, that's the idea. This is the idea. This is why I call myself JC frickin' practices. JC does not video edit. This is live video editing. Like, it gets some of the interesting, attention grabbing, there's something visually cool happening, but it's all live, dude. That's awesome. Okay, so somebody asked, what is Fang? Facebook, Apple, Amazon, Netflix, Google. In other words, big tech. Software engineering, like the biggest tech companies in America. I worked at Apple. I also worked at Google. There's people have also said Fang Mula. Fang Mula is also a thing. Fang Mula includes Microsoft, Uber, Lyft, and what's the last one in Fang Mula? Apple, Amazon. What is the last one in Fang Mula? Apple, Amazon, Airbnb? Maybe? I think it's Airbnb. Anyways, I just want to point out, I also worked at Lyft as well. So I'm triple Fang Mula or double Fang, whichever you prefer to think of, but software. JC Practices would also be a good law firm name. Yeah. practicing law, practicing whatever. Life is about practice, everybody. I really think building skill and focusing on skill and getting good as hell at something, like developing a craft, dude, and just getting into that mindset, that's, I feel, the key. Okay. Yeah, I don't care about shorts, man. It's very low quality attention. Super low quality attention, high effort, and very low value to me. Oh, I'm sorry that you suffer from short-term memory loss. That sucks. I'm sorry to hear that. Okay, so now we have our eigenvectors. Therefore, we claim that D being -1 and 10, and C being, well, if I normalize this vector, let's see, 3 minus I. Here we need, when we find the normalization of this vector, we need to multiply by the conjugate, don't we? Right? If I normalize a complex valued vector, so the dot product of the first with its conjugate, yeah, this is the dot product is extended to the inner product, or the, yeah. That would be 10 plus 1 square root of 11. And then and again we get 10. So we get the length of V1 is square root of 11. So then here I'm trying to write V1 normalized and V2 normalized. It's going to be 1 over square root of 11 times the matrix with the eigenvectors in the column vectors. So 3 minus I, 1. 3 minus I, 1 in the first column. And then in the, oh, that's the second column, my bad. First column is 1, -3 minus I. -3 minus I Now, a question is, does C is supposed to be unitary? Does U equal U conjugate transpose? U conjugate transpose is 1 over square root 11. The conjugate of this is 1, 3 plus I, negative 3 plus I, 1. So why do I feel like something is uneasy? Like I'm a little uneasy about this. This is not the same, right? Do they need to be equal? Oh, no, it's not that they're equal. We need the inverse to be equal to the conjugate transpose. Yeah. Then U times U conjugate transpose is 1 over 11 times now this is starting to look correct. Negative 3 minus I, 3 minus I times here we have 1 plus 3 minus I times 3 plus I. Well, 3 minus I times 3 plus I is 9 minus I squared is 10 plus 1 is 11. In the top right, we have negative 3 plus I times 1 plus 3 minus I. Negative 3 plus 3, I minus I. This is 0. Bottom left, similarly, same reasons, is 0. Bottom right is going to be 9 minus I squared is 10. 10 plus 1 is 11. And voila, this is the identity matrix. So, yep, that's correct. So therefore, U is indeed unitary, as we expected. And the last thing to check is that D equals U inverse A U. This is true if and only if UD equals AU. So we can check this. Let's just copy this whole thing. Here's U. And our diagonal matrix was negative 1, 0, 0, 10. So if you multiply by a diagonal matrix on the right, you scale the rows. Yeah. So -1, -3 plus I, -30 minus 10I, and 10. So that's UD. What is AU? Let's commute that 1 over root 11. A, what is A again from the beginning? We've got this. Oops, did I copy that? Dang it, come on. Copy. Oh wait, we do still want that 1 over root 11 here. U, looking in the previous line, was 1, 3 minus I, -3 minus I, and 1. Let's use the next line. We've got 9... 3 minus I times -3 minus I. Well, if I factor out a negative from the second term, then this becomes 3 minus I times 3 plus I, and that, like we've found a few times, is 10. So 9 minus 10 is -1. Matches in the first element in both matrices. Then top right corner, we've got 9 times 3 minus I plus 3 minus I. 27 plus 3 is 30. Minus I, wait. Yeah. 27 plus 3 is 30. Minus 9I minus I is -10I. In the bottom left, we have 3 plus I plus 0. Am I missing a conjugate transpose sort of thing somewhere? Yeah. Did I copy you correctly? Okay, something feels off, but nonetheless. We found AU to be that. So what went wrong? Oh, I just did my multiplication wrong, didn't I? I did do my multiplication totally wrong. Yeah. I screwed. I did not do this right. These should be scaling the columns, shouldn't they? Yeah, it's multiplying on the right scales the columns. Yes. Top row dot product first column is -1. Second row dot product first column, we get 3 plus I. Oops. And then first row dot product second column is 30 minus 10I. 30 minus 10I. And then second row dot product second column is 10. Now these match. Yep. So, yep, they do match. I could say, so UD equals AU. Right there. We got it. Yeah, I found it. I eventually found it, dude. Yeah, I eventually found it. I'm trying to finish these problems before reading chat, but you can see how many times I make errors. Dude, if you filmed yourself doing math, I'm betting that you would make just as many errors as I do. You know, I'm not going to beat myself up about it. I think we all make these little errors all the time, and most people just don't film it, right? Most people don't film it and share those little moments in your notebook where we make silly little errors, right? I found it eventually. Which software am I using for writing? I am using Notability. It's a great app. I'm trying to catch up with y'all. I'm glad that you're chatting amongst yourselves. That's really good for my engagement. And it's really good for building community, dude. Even more importantly. Whoa, geometric algebra for computer science and geometric algebra for computer graphics. Cool. All my homies hating on the most widespread area of math to ever exist. Linear algebra is the greatest math, dude. It's the greatest math. It's the best math. Yeah, my bad. Multiplying by a diagonal on the right scales columns. How can I... Okay. Left and right. You know, first and second, rows and columns. Multiplying by a diagonal on the right scales not rows, but columns. Like rows, then columns, Aij. Multiplying on the right scales columns. There we go. Maybe I'll try to remember that. I try to get too fancy and too slick trying to jump right to that instead of doing it immediately. Or just doing it, in the straightforward way, one at a time. Yeah, I caught it. I caught it eventually. I don't need to film myself to make errors. Well, yeah, I think I would make fewer errors, but I would still make that error. Like, I don't feel like the stream is adding that much extra stress and likelihood for errors for me. Like, maybe some, yeah, because I'm explaining out loud, but I literally don't care that there's a camera on me. Like, because I've practiced that a lot. Like, during the guitar stream, like, it doesn't, I forget that you all are there. But if I were doing this on paper, it's cleaner and easier for me to write. Like, I can see more lines at once. I'm not zooming in and out and stuff like that. And I'm not explaining out loud. You know, I might have caught that the first time through if it were paper, but Sundar, I think I missed you, but enjoy whatever you're eating. Good to see you. What is 160? Oh, for the JE? You're talking about scores? 160, dang. Translation between matrix multiplication to function composition is conceptually simple but computationally annoying. Yeah. Okay, so let me try to think of it that way. Let's make up some numbers, y'all. 1, 2, 3, 4, 5, 6. Right? This is going to take the basis vectors five, 0, and 0, 6, and we're going to scale these, right, to add from V1 and V2. Scaling by that matrix maps to a vector which is one times the first vector plus 2 times the second vector. Is that correct? For the first column vector. 5 and 15. Let's see. 2 times the second vector. 13. No. Trying to think conceptually of how to see. So V1 goes up to V1 prime somewhere up here. I need to rescale everything for it to look realistic, but 5, 15, and the second one, 12, 24. I don't know. I'm not great at seeing a matrix as a combination of the vectors on the right. I'm just not, I don't know, I'm just not great at seeing it. Like, how do I get... This is A11 times vector so it takes like parts of okay, yeah. So it is B1 times the column vector A11, A21 plus B2 times the column vector A12, A22. Okay. So 5 times this column plus 0 times this column is the first column of the new matrix. And then 0 times the first column plus 6 times the second column gets us the second column of the matrix. So, okay. I think now I can see that this is a linear combination of the columns of the first matrix, but I was expecting to write this stuff as linear combinations of the column vectors of the right of the second matrix. I think I see it a little bit better. Yeah, JEE is a college entrance exam in India. It's like the biggest college entrance exam, really intense, high expectations, lots of pressure to do well on it so that people can get into the best universities. Arad, where are you from, bro? I forget. Did you say Vietnam earlier? Somebody said Vietnam. Oh, Ta said Vietnam, and you're in Israel. Cool, man. Cool. Yeah, so much diversity in this freaking chat. I love it, dude. Love it. Okay, so we found our diagonalization, and we're done with yet another computational linear algebra problem. Heck yeah. 9.4, Jordan canonical form. This is the last section of this chapter. Whew. I don't really remember this super well. So we're going to find the eigenvalues of a matrix. We're going to give rank and nullity of j minus lambda to the k for each eigenvalue and every positive integer k. Draw schemata of the strings of vectors in the standard basis arising from the Jordan blocks in J. And then for each standard basis vector, EK, express JEK as a linear combination of vectors in the standard basis. Where J is -1, 0, 0, 0, 0, 0, 2, 0, 0, 0, 0, 1, 2, 0, 0, 3, 2, 0, 0, 0, 0, 1, 2. Okay. So J is... I think that the book uses this notation that I'm about to write. Like J as an array of JI blocks. Maybe not. They read it this other way. Yeah, I'll just keep it. So J is J1, J2, J3. There are 3 Jordan blocks where J1 is -1, is just -1. J2, here, let's clean that up. J1 is a 1 by 1. J2 is a 2 by 2. 2, 1, 0, 2. And J3 is, again, the same thing. 2, 0, 1, 2. In part A, we find the eigenvalues by solving PA lambda equals 0. It's an upper triangular matrix, so we have 1, 2, 3, 4, 5 negatives that I factor out. Lambda plus 1. -1 minus lambda, yeah, factoring out a negative is that. And then lambda minus 2 to the 4th. Therefore, we have 2 eigenvalues with different multiplicities. So this was part A. And when I said multiplicity 2, I meant multiplicity 4. Okay. So that was part A. Give the rank and nullity of j minus lambda to the k for each eigenvalue and every positive integer k. How do I do that? Part B. Rank and nullity for j minus lambda to the k for all eigenvalues and for all integers. Positive integers, I guess? Yeah, positive integers. Or non-negative integers, at least. No, it says positive integers k. I've never even heard of Ludo. What the heck is Ludo? Any of y'all into gaming? Nah, not me. So, for lambda 1, j minus lambda is... Lambda 1 is -1. So along the main diagonal, I subtract -1. Subtract which ones we've already done. Subtract -1 from all the others. These are all going to be 3s. I believe that every time we're going to lose 1 from the rank and gain 1 in the nullity. I don't know if I'm supposed to literally just do all the multiplications. Oh, wait. This entry with this one, the last column should be a 3. And I have a 6 where there should be a 3, right? Oh, wait, no. No. Nope, the 6 was fine. This is a 6. Math is hard. Math is hard. Oh, maybe it... I think it preserves this structure for all positive integers k, doesn't it? Yeah, it does, doesn't it? Rank. J minus -1. Huh. Is that what I expected? I don't really have a proof, but I see that the structure is preserved from then on and the exact same matrix multiplication moving forward will always just keep increasing the main diagonal entries and yeah. I guess I could just argue that the bottom triangle is always 0 and the main diagonal always has 0 followed by 3 to the k. Okay, then we have j minus 2i to the k. Let's calculate the first one. Well, let's copy the whole matrix. So J minus 2 this is J, so if I subtract 2, get that. And zeros along the diagonal. Then, I feel pretty confident that rank is 1, nullity is 4. For all positive integers. In fact, I think when we square that matrix, we just have 9. We get -3. Oops. -3 to the k. And zeros everywhere else. I'll just write a giant 0. For all integers at least 2. Yeah. Neat. I need to learn more about Jordan normal form, I think. Oh, I already read off the eigenvalues pretty much directly, right? So next, draw schemata of strings of vectors and standard basis arising from Jordan blocks J. So I think that this is saying to calculate J1E1, J1 E2, J1 E3, J1 E4, J1 E5. We're going to draw schemata of strings of vectors and standard basis arising from Jordan blocks of J. Um, man. Okay, so of the strings of vectors in the standard basis arising from the Jordan blocks in J. Do we do this for every Jordan block individually? I think so. So J1 is here. We wrote these here. So J1, E1. Wait, for the standard basis vectors, is this the right way? Is this what I should be doing? Or should I be analyzing? Yeah, I guess J1, E1 is negative E1. And that's the only standard basis vector for block J1. J2, E1, is 2, 0. J2E1 is 2, 0, which is 2E1. J2E2 is E1 plus 2E2. Is that right? E1 plus 2E2. Wait, J2E2, 2, 1, 0, 2, 0, 1. Yeah, is 1, 2. Is E1 plus 2E2. Correct. J1, oh wait, no, sorry. J3E1 is 2E1, and J3E2 is E1 plus 2e2. So, yeah, J3 and J2 are identical, so I should have just said the same. Now, draw schemata of the strings of vectors in the standard basis arising from the Jordan blocks in J. Okay. So J minus lambda I think that this is what I'm supposed to be drawing. I think that this is what they want me to see. The first eigenvalue was -1. Oops. So this one should have been J1 plus I maps the first basis vector to 0. J2 minus 2I is the same as J3 minus 2I. and they map E2 to E1 to 0. Yeah. Cool. And then part D, express JEK as a linear combination of the standard basis vectors. Uh-huh. So J plus I will map E1 to 0, J minus 2I gets us, I believe, E5 to E4 to E3 to E2 to E1 to 0? I'm learning this stuff for the first time, y'all, so I am not as confident as I'd like to be about this. Dude, I don't know what's going on here. Not as confident about this at all. I think at this point, I'm supposed to just find all our matrix J is this. And yeah, J2 is 2 E2. Yeah. I think that this is what this last part was asking for. It's just compute the action of J on every basis vector. And that's it. And express each one as a linear combination of basis vectors. So I'm pretty sure that's it. Sorry about the lag that happens. It happens. Projective geometric algebra. That stuff sounds pretty cool. Yeah, so good that they can't ignore you. Yeah, it's a great book, bro. This is a fit. You could read that. You could read. If I like look away, and it zooms, focuses on the back. It's a fantastic book, bro. Fantastic, fantastic book. Yeah. Well, I'm sorry, dude. Like, that sounds like some pretty frustrating experience that you're having. Okay, cool. I think... Oh, this is an odd problem, so I can check the back of the book. Thank you. Thank you, Fraleigh, for this. It's very good for us self-studiers. Chapter 9. We're almost done. Okay, so J of E1 is negative E1, J2, JE2 is 2E2, JE3 is E2 plus 2E3, JE4 is 2E4, and JE5 is E4 plus 2E5. I got it. And then part C, is this what they wanted? J plus... Okay, this is true for J, not just JI or J1. E1 maps to 0. J minus 2I. E2... Or E3 maps to E2 maps to 0. E5 maps to E4 maps to 0. Okay, so I found this for the individual blocks, but then because it's true for the individual blocks, then J plus I is going to map E1 to 0. J minus 2I has two schematic strings. One of them says that E3 maps to E2 maps to 0. And then also E5 maps to E4 maps to 0. And so that's just extending these Jordan blocks to fit in a 5-dimensional matrix. And then this is therefore true. Neat. Okay, so this, to any positive integer k, let's see. I think that we should have had rank is 5, nullity is 0 if k is 1, rank is 4, nullity is 1, when k is greater than 1. And then similarly here, we I got this ever so slightly wrong. So J minus dang it. Oh, this was supposed to be J plus I to the k to the kth power. What I found was J plus I squared here. J plus I to the kth power always has rank 4, nullity 1 for all positive integers. And then J minus 2I to the kth power This has rank 3 if k is 1. Rank 3, nullity 2. When k is 1, and it has rank 1, nullity 4, when k is greater than 1. So I got this just slightly off. Yeah. But I got the basic argument about these correct. I just didn't handle the case of k equals 1. Or I didn't write it down correctly. Hey, Levi, what's up, bro? It's been a little bit, dude. How are you? How's it going, Levi? Okay, I gotta wrap this up. We've been going for a while now. But yeah, y'all, I had a pleasure practicing, and I don't think last time that I worked through chapter 9 that we got to Jordan, to the Jordan form, Jordan canonical form. So it's super cool to be making some progress again in section 9.4. Thank you for watching. We've got one more day in this book, and then we will be switching over to representation theory for 4 streams in a row. In Twitch, we got somebody in Twitch. How's it going? Slight GPX2. Can you check the book Group Theory by Kurosh? I like it. Just check the content table. Yeah, for you, since you're new, you have to hit the follow, though. Let me know if you're still there. And hit the follow, bro. Kurosh Group Theory. Theory of Groups by Kurosh. I've never heard of it. Never heard of it, if I'm going to be honest with you, dude. The Theory of Books by Kurosh. Yeah, let me just check the table of contents. So, definition of a group, subgroups, normal subgroups, endomorphisms, automorphisms, groups with operators, series of subgroups, direct products, defining relations, free groups, abelian groups. Yeah, man. I mean, this looks like a pretty good book to me. Like, it's all focused on group theory, isn't it? I like group theory a lot, man. Like, I really like group theory. I think it makes sense to study abstract algebra just totally focused on group theory for a while and do, like, an entire book on group theory before adding ring theory and other abstract algebra. Yeah, there's some topics in here that I don't feel like I'm super comfortable with. There's a lot of stuff I'm not super comfortable with. It looks pretty good. I think that you'd need some math background before you can jump into this book. But it looks like it's like kind of at the level of Dummett and Foote. But it's the entire book is on group theory, whereas Dummett and Foote is like an encyclopedia of all group theory, ring theory, module theory, tons and tons of stuff. Yeah, it looks nice. It looks like a nice book, if you ask me. Yeah. Ooh. There are a lot of good examples from different categories, and I like to find examples from algebraic topology for some concepts. It starts very friendly. It looks very nice, dude. It looks very nice. Yeah, man. Looks like a nice book, for sure. Hey, what's up? Hikari, how are you? Y'all, I've been practicing for a while today. I gotta wrap it up. Thank you for watching. It's been a pleasure. Please do like and subscribe. I'm available primarily on YouTube, but now I'm starting to stream to Twitch as well. So if you're following me on YouTube and you prefer Twitch, follow me on Twitch. If you see me on Twitch and you prefer YouTube, follow me on YouTube. I'm just multi-streaming to both. I also have a second channel in classical guitar. All of the music we've been listening to are my recordings as a classical guitarist. So check that out. This is a second channel in YouTube, and it's just called jcpractices. The display name also says jcpractices guitar. Let's see, what else? I've got a Discord, bro. Join the Discord. And I want to build up a really cool community of math hobbyists. People who are studying math because it's beautiful, because they enjoy it, because it's fun. So if y'all want a nice community, come join us in the Discord, dude. It's a nice place. What else? Related to that, I'm starting a math hang on Sundays. Zoom, Sundays, not 10, 9 a.m. Eastern. I'd love to see you there, y'all. I really enjoyed this math hang that we did yesterday. I did a little intro to proofs with high school mathematics. So if this sounds interesting to you all, I'm going to begin intro to proofs with high school math, middle school and high school math. And this is going to become a series here on this channel. Thanks, everyone. And the gaming channel as well. Yeah, well, the gaming channel's not really very active. Yeah. Thanks for handling a couple of messages, Lockheed. Good call. Keep it all, moderated, and keep it chilly, everybody, and protect your privacy. Yeah. Don't share exactly which school you go to. I mean, I don't know, it's probably not a big deal, but still, social media can be weird. I think that's a good idea. Okay. Thanks, everybody. Thanks, mods, for helping keep chat organized and everything. All right. Take care, everyone. This was super fun. Man, 3 hours today. Damn, dude. Thanks, Geometry. I hope you tune in every time I stream. That's awesome to hear. No, I'm not Korean or Japanese. I am American. I'm American and Latin American. Yeah. All right. Thanks, everyone. Take care. Bye. Bye.